So we are talking about electrochemistry. And electrochemistry is, I don't know, often neglected, I think, in its power. Because as we're going to see, you can, just with a very simple little sensor, you can monitor anything you want inside like a living cell or living organism or the stomach or the brain or whatever you're looking for. It could be looking for an enzyme, a protein. It could be looking for a metal. It could be just leave your imagination to it, and you just got to develop the stuff. And there's simple things with electrochemistry, like if you've ever done some fence work, right? You wouldn't want to use this kind of nail. It's just going to rust on you. You'd want to use this kind of nail, right? They've both been soaking in water since 2011. So what is this kind of nail? They're both iron, zinc plated, right? So the water is actually reacting with the zinc first. And once all that silver kind of color is gone, then it'll start looking like this. It's already starting to. Right, I can see the top is starting to get a little tarnished looking. This used to look brand new in there. I should throw another one going in there. Okay. So that's what's going on with all these boats, right? That's why they're putting these sacrificial anodes on there, because those boats are billions of dollars, and you don't want them to start rusting. So, all right, you can see them. Okay. Okay. So we're going to first review a few things. Assignment of oxidation numbers, see if you remember what that is, right? Determining oxidizing, reducing agents in their reaction. Okay. And here's a typical handout on determining oxidation numbers. And the whole idea is there's so many electrochemical reactions, and all these sensors are pretty much electrochemical. And there's this transfer of electrons going on between one compound and another. Something's donating them, the other compound is accepting them. And they're called redox reactions, right? And they happen all over the place. And to keep track of this, what's going on, they use some electron bookkeeping. So we have these rules to assign all the different elements a certain number, and then that number is going to change depending on whether the electrons were donated or accepted, and therefore. So the rules look pretty complicated, but I think you might remember them, right? Determine the oxidation number for each element in each compound. If you remember that, let's just see. Victoria. Let's see what Victoria remembers. Now, I'll get you started here. It's not much of a hint, though, Victoria. We have one potassium and one chlorine. The oxidation number of all the atoms present, the potassium and the chlorine, have to add up to be the overall charge. And the overall charge here is 0. I don't know if that helps you much. But what is the oxidation state, the oxidation number you would assign to these? Yes. Very good. Okay. So if you remember, a lot of that stuff that I've been harping on for compounds, right? This group right here can only form what? Plus 1. Plus 2, right? So that's really going to help you. And if K is plus 1, chlorine has to be -1. Okay. Here's some more. We'll do some more practice. And how about nitrate? Okay. Now there's a spot, Eustacio. You have to start somewhere. Where did he go? Oh, he's not here. Albert, poor guy. You got to start somewhere. And in the rules, if you can dig it out, or you might remember, which element do you start with? And it's always this number. Which element? Oxygen. It's always what? -2. Okay, in my little notation here, I'm circling my oxidation states. So I'm circling it. Okay. Yes, because I have 3 oxygens. So I actually have a -6. But I'm not circling the -6. My oxidation state for oxygen is -2. So that's why I'm circling it. Okay. But I actually have a -6. You're right. So N has to be, Sochi, what does N have to be? There's only one of them. Has to equal the -1. So N would have to be 5. Everyone see that? N has to be 5. Because a +5 and a -6 would give me -1. What if I would have had a, well, we'll do some more. There's a handout. So pretty much for me what this rule boils down to is just remember oxygen's -2 and then the sum idea. Right? You add up all the oxidation states, you better get the overall charge. And if nothing is written there, what's the overall charge? 0. Okay. Okay. Oxidizing agents are always, Kevin? Oxidizing agents are always, what?
Reactive.
Yes. And they always get, Jamie, oxidizing agents always get reduced. Yeah, it's an oddball. You just got to remember it. Oxidizing agents always get reduced. Now, let's back up here. First, Marlena. Let's say I have Cl2, right? What's the oxidation state of chloride? Right on this side. What is its oxidation state? It has to be what? Has to be, anybody help her? Has to be -1, because everything has to add up to be the charge, right? So it has to be -1. What is chlorine over here? 0, because it has to add up to be the charge. 0, right? So chlorine, its oxidation state got oxidized or reduced. Javier, what happened to it? It got reduced. It got more negative. That's the reduced, right? Going this way, it got oxidized. So chloride got oxidized. But we're always thinking of reactants going to products. So chlorine got reduced. Reducing agents are always what, everybody? Reactants, and they always get oxidized. Okay. Determine the oxidizing and reducing agent in the below reaction. Okay, Destiny. We don't have any choice here. Let's just figure out these guys first. What could we do first? Oxygen should be what? -2. So my total will be -6, right? Okay, so sulfur has to be what, Alyssa? +4. Okay. So we don't need to mess with chromate. Let's just figure out what sulfur's doing on this side. Because if we know one's the reducing agent, the other one has to be the oxidizing agent, right? So Daisy, let's figure out the chromate here. -2 on the oxygen, good. So you'd have a what for the oxygen total? -4 times -2, -8, okay. So chromium would have to be what in a -8 would give you a -2? +6. Yep. Okay. Oh, I just said we didn't have to worry about this, so why am I doing it? That sucks. All right. Well, you guys needed the practice, right, Andrew? Okay. So let's do sulfate then. Yeah, let's figure out what sulfate is. -2 on the oxygen. -8. So sulfur has to be +6. Okay. Now we have enough information here, Jose, to say what's the reducing agent, what's the oxidizing agent. This compound is the what? This compound got oxidized, so it's the reducing agent. Exactly. This is the reducing agent. This has to be the oxidizing agent. So it got reduced. So you can figure out what chromium is. I'll guarantee it's less than 6. Okay. Charge, current, voltage, and power. What's the standard metric unit for each? No name. Uh-oh. Bradley. Well, charge. What's the standard metric unit for charge? Remember?
Was it current?
Well, no, current's going to be the next one. Charge was just, does anyone remember this? Here's its symbol.
Oh,
Coulombs. How about current? Amps. Voltage, Jessica. Big V for volts, right? How about a power? Brandy, how about a power? Watts. Okay. Oh, I guess I could. I'm doing both these at the same time, aren't I? Oh, big W for watt. Okay. Well, we should know what a watt is. What's watts? Give you a hint. It's energy consumed per unit time, or energy produced per unit time. Joules over seconds. Good. Okay. What's a mathematical symbol? Oh, for charge, we don't use C for charge. We use that little Q. Yeah. Current, we don't use big A. That capital I. Good. But voltage, we use big V. Power, what do they usually use for that? I don't know if I have any equations written. Yeah, there it is. Big P. Okay. Current, Matt, is charge per unit time. Therefore, an amp is a what over what? Coulomb? Yeah, coulomb over second. Coulombs per second. Nice to know, because these things sound like they're coming out of nowhere, but you need to know this to get through the homework. You need to know that amp is coulombs per second. Just like any equation, if you divide the number of coulombs by the number of seconds, you will get current. Okay, so realize that's how a lot of this stuff is working. Voltage is electric potential energy per unit charge. Oh, okay. Sochi, what would be the units for a volt then? Electrical potential energy per unit charge. Not over Q, over C. What's energy? Standard metric unit for energy. Someone told us already. Yeah, joules. Joules per coulomb. So voltage is an odd thing. Electrical potential energy. There's a heck of a lot of electrical potential energy at the end of this. It's so high that it's actually ripping the air apart. And that's how you're hearing that sound. That's the air falling back on itself. It's actually torn apart. And that's really what lightning is, right? It rips apart the air so that current can actually get through it. Air is an insulator, right? But I don't have to do this. Electrical potential energy, right? There's a lot of electrical potential energy or potential energy here the closer you get. So you can't really see it until you get closer, All right, you can see it's starting to accelerate and hit the fluorescent material inside the bulb. All right, it's better if the room is dark, but okay. I hate playing around with this thing. I haven't got shocked yet, though. Okay. A Faraday. F equals the total charge on 1 mole of electrons. Man, if you remember this, you're doing pretty good, Kevin. 1 Faraday equals, it's going to be a number.
It's the times 10 to negative 19 over, but the actual answer is times 10 to the negative 4. 1.964.
I'm going by memory here. I thought it was 96,485. That's not right?
Yeah, I think it's I thought it was, because it's,
Do I have it? Let's see. Do I have it on the handout?
24.
Somebody's got it. I don't have it up there. 1 Faraday is 96,485 coulombs. Wow, someone's got it. I'm pretty sure that's right. Okay. So it's the charge on 1 mole of electrons. Yeah. So smartphone. Okay, 96,485. Typical relations. Voltage is current times R is. We didn't mention this one. I don't think we're even going to need it. Resistance, but I don't think we'll even need it. Power is current times voltage. Work is voltage times charge, right? So you have this electrical potential energy field, and you're actually moving the charge inside it. Either it's being pulled or pushed. Galvanic cell. So I think this is where the real meat is. Okay. The other stuff was kind of anecdotal, and you might need pieces of it. The electrochemical cell to the right can be described by the reaction. I had to change a few things. This doesn't quite match your handout. But so there's our reaction. Zinc solids reacting with copper, forming copper solid and zinc ion. Okay. After everything gets connected and the light bulb in the diagram lights up, is the system at equilibrium? Right? Javier, can you imagine that happening? Right? You just got to pretend, I guess, and ooh, little light bulb lights up. Is it at equilibrium? What do you think? Anybody dispute? Right? The reaction is progressing. The electrons are, right? The zinc's being converted to zinc plus 2. The copper plus 2 is accepting electrons, forming copper solid. And the electrons are passing through here. Right? So they just really slowed this reaction down so that they can make use of it and do some electrical work. So no way is it at equilibrium. The reaction's proceeding. In fact, you want it to be very far away from equilibrium, have a whole lot of reactants and hardly any products so that the reaction will progress. Right? So definitely no. Okay. As time progresses, what will happen to the light bulb, Angelica? What will happen to the light bulb in the diagram? All right. As time progresses, yeah, the little guy should just get more dim, right? You're going to have less and less reactants. So it's just going to get less and less, get more and more dim until finally, and what should happen to the little voltmeter reading? It'll go down. Right now, can you read what it says? Yeah, it says 1.08 volts right now. Okay, so that'll go down. Just like a battery, right? It'll go down over time. Okay. So when do you know equilibrium is reached? Say it's dead, right? Yeah, light's gone. Okay, there's no voltage. What is the oxidizing agent in the above reaction? A little more practice here, Destiny. What's the oxidizing agent? What's the oxidizing agent? Oxidizing agent has to, otherwise I can't figure this out. Oxidizing agents have to get reduced. So it has to be one of these. So what's getting reduced? Zinc is going to zinc plus 2. That's getting oxidized. So it's got to be the copper plus 2 because it's getting reduced.
It's just backwards.
Yeah, so everything had to change. What's in yours isn't correct. I noticed that this morning. Okay. It really doesn't matter because we're not going to use that information anyway, but I didn't like having something wrong on there. Recalling from past hold it. Oh, we already did that. So we are right here. Recalling from past chemistry classes, what was an easy way to get delta G for a reaction? So here's a reaction. It doesn't have to be electrochemical. You can get delta G for any reaction, assuming you have the right table. How the heck? Alyssa, what are they talking about? Get delta G for a reaction? It's supposed to be easy? What do we do? No. That's the hard way. One of the hard ways. There's more than one way. Using a table. The table had to have what? A delta G for every single compound in the reaction, right? And then you added them all up for add up all the delta G's for the what? The products. And then you subtracted them out for the reactants. Remember doing that? So you had to add up the delta G's for all the products, subtract out the delta G's for all the reactants, and you got delta G for a reaction. Okay. We did that. We did that for delta H too in general chemistry. See if you remember this. The Gibbs free energy, it was called, Daisy. The change in Gibbs free energy, delta G. It's always what for chemical processes that will definitely happen, including galvanic electrochemical cells. Delta G is always negative. Very good. She remembers that. Okay. Only for electrochemical reactions does delta G, the Gibbs free energy, equal minus NF E cell hold true. What's the numerical value for E cell, Jose, in the photo above? What's E cell? What is it? It's the voltage. E cell is the potential. E cell is what the voltmeter reads. Okay? It's what the voltmeter reads. So if a cell is galvanic, that means natural, it's going to happen. That E cell Brad number needs to be what? Right, looking at this equation, delta G has to be negative for it to be natural or spontaneous. Well, E cell would have to be positive. Right, because then you have a positive times a negative, you get a negative number, it'll work. Well, what the heck is that F doing in there? What's that F? Another no name. Faraday's constant, 96,485 coulombs per mole of electron. And I think this is coming up. We might as well just mention it now. What's N? It's number of moles of electrons, right? Because remember, F is 96,485 coulombs per mole of electrons. So you have to get those moles of electrons to cancel. So however many electrons, moles of electrons are passing through here, that's your little n. Okay? That's the number of moles of electrons to actually pass through. And this is where, I don't know, electrochemistry is probably so old, that's why I get so verbiaged up. Cell potential, the same as cell voltage, which is the same as electromotive force, which is the same as EMF, which is the same as E cell, right? They're all what the voltmeter read. They're all volts, okay? So just try to remember that, because that will help you. Standard reduction potentials. Okay, So what they did is they took all these half reactions and, well, we should start here. When all concentrations are, Jessica, all gas pressures are something, the temperature is something. The potential is measured against an SHE, a standard hydrogen electrode. The table of standard reduction potentials can be prepared. What they're doing here, Jessica and everybody else, is here's 1/2 the cell. Then they have their salt bridge coming over to another cell, and it just contains this stuff. And then they had a voltmeter in there, and they measured it. But they had to fix all the concentrations, the gases, pressures, and the temperature. What are those? What would you guess? What concentrations? I don't know if it's much of a hint, but it's the standard conditions. Does anybody know? Concentration is 1. 1. Pressure is 1. Temperature is 25. Okay. And then you get these standard reduction potentials. Okay. And they set this one to 0. So whatever the voltmeter actually reads, they just, put it on the table. So notice if both of them were the standard hydrogen electrode, you just get 0. There's no potential difference. You have the same thing on both sides. So it's just 0. So some things give more positive, some things give more negative. There's a lot of chemistry in there, and that's what I want to see if we can dig out. For all electrochemical reactions, we have this relation. How can this relation be written for when the electrochemical reaction occurs under standard conditions? Standard just means you add a little what superscript? Remember this? A little 0. So when you want to put a little 0 here and a little 0 here. It doesn't make sense to put a little 0 on F because F is a constant. It doesn't make a little sense to put a little 0 on the N because the N's the number of moles of electrons, and that's going to be different for the different half reactions. Okay. So both reactions are valid. It's just when you're talking about standard conditions, then you have to put in those superscript zeros. So how is a table of standard reduction potentials used to get this? Since you have a 0 here, that means standard conditions, you have to use a table, right? It's just like when we said, hey, we can calculate delta G using some simple thing. Remember back here? Oh, man, it's way back. Where'd that go? Right, yeah, in general chemistry, where did it say that? Here it was, right here. So when you calculate that delta G, doing products minus reactants, you have to technically have a superscript 0 there. That's all standard conditions. Okay. Pretty much anytime you use a table, you're using little superscript zeros. So how is a table of standard reduction potentials used to find E0 cell? Okay. I think we just go ahead and just do this EX1 and we'll figure it out. Because delta G0, we said, was minus NF E0. Right? So we need to find all this stuff. All 3 of those. We know what F is, but we don't know what the other guys are. So does anyone remember how to do this? Right? We had to break it into its 2, what were they called? Half reactions. Okay, one of the reactions has to be producing electrons. The other one had better be one's producing, the other one's reacting with them, right? So one's accepting them, one's giving them up. Otherwise, and the electrons cancel. Remember doing that? Otherwise, things are messed up. So pretty much you write copper plus 2 here, and what it's turning into over there, right? Nickel solid here, and what it's turning into over there. Okay. And I really believe our half reactions aren't that complicated. In fact, we can pretty much just copy them from our tables. They were getting much more complicated in general chemistry, but pretty much you have to, if you remember the steps, you can either copy it from the table or just remember the steps. You balance everything but oxygen and hydrogen. Then you balance, right? And then you balance the oxygen by adding H2O. Then you balance the H's by adding H+. Then you balance the charge by adding E minuses to the most positive side. I don't think we're going to do all that. We pretty much just copy it from the table. But if you do, you might want to Google that up, right? And over here, you'd have it over here. So if you add it up, the electrons will cancel, and we'll get it right. But we need to write our E zeros. Okay? So our copper half reaction, where is that? It's right here. But we have copper plus 2 going to copper solid. Here we have, we have copper plus 2 going to copper solid. That's the same. So copy it. Positive 0.34. Okay. Nickel solid going to, oh, here it is. Nickel solid going to nickel plus 2. It's right there. But it's flipped, so I have to do what to the E0? Change the sign. Good deal. So that's a 9, that's a 5. Oh, that's a 9, that's a 5. 0.59 volts is my E0 cell. Okay. Hey, do you remember if, sometimes if, do you remember playing this kind of game? If this guy was like a 3, then you had to multiply this one by, yeah, okay, you remember that. Good. What do you do to these numbers? No, you don't do anything. These are potentials. So it doesn't matter how much of the stuff you have. It's a potential. So you leave it alone. Okay. All right. But anyway, so we have our delta G0. Whoa. Our delta G0 is minus NFE0 cell. So what do I put in for my N? I should put it back how it was. The number of moles of electrons that canceled out to get my overall reaction. And in this case, it's going to be 2. F was 96,485 coulombs per mole of electron. My E0 cell is 0.59 volts. Okay. So coulombs times volts is energy, joules, and I'll get my answer. Okay. And it's negative. So is it natural? Is it spontaneous? Yep. Good. Okay. In a table of standard reduction potentials, all the reactants are, let's find a table. Here's a table. Table of standard reduction potentials. Or you can go back and see it better, it'd be bigger, right? It'd be bigger. Here it is. All the reactants are what? The question is reducing agents or oxidizing agents, right? Yeah. All the reactants are what? Every single reactant is getting oxidized or reduced. Every single reactant is getting reduced. Nickel plus 2 to nickel solid, tin plus 2 to tin solid. They're all getting reduced. Right? These are all, and it kind of makes sense. It's called the standard reduction potentials, right? So yeah, everything's getting reduced. So all these reactants are what agents? Oxidizing agents. They're all oxidizing agents. All the products are reducing agents. They're not going to give you two tables. They're never going to give you a table of standard oxidation potentials. They have to just realize, oh, if I flip this, I flip the sign. Okay? So they're only going to give you one table. But all the products, all right? Whoop, I circled it twice. All right? Okay. So these guys, the products, they're getting reduced. Every single one of them. So they're oxidizing agents. Right? Go the other way, they're getting oxidized, so they're reducing agents. Which is a stronger oxidizing agent, iodine or tin plus 2? Okay, let's clean this up. Iodine or tin plus 2? Here's iodine, and here's tin plus 2. First, are they both oxidizing agents? Yeah, right? Because we don't want to make it a trick question, but yeah, they're both oxidizing agents because they're both getting reduced. So we can compare them. Which one is stronger? Now, I don't know if you see the answer. This is the answer. When you find out any overall reaction, you're just adding up the potentials. And you want E cell to be really what for it to be natural? E cell needs to be positive, right? E cell has to be positive. So the more positive these are, whether this top half reaction, copper plus 2 is getting, this is getting reduced or oxidized. It's getting, copper plus 2 is going to copper, it's getting reduced. It's a plus 2 here, it's a 0 here, it's getting reduced. So this is a really natural process, positive 0.34. The other way around, not so much so. Nickel solid going to nickel plus 2, it's getting oxidized. Again, it's a positive. So this is going to be a very natural and spontaneous, it's going to happen. But it doesn't mean that copper solid going to copper plus 2 won't. As long as you're adding to something that'll take over and make the overall reaction positive, it'll be natural. So that's the game we're playing. So when it asks, is iodine or tin stronger, you would say iodine, because look at that positive 0.53, right? Okay. How about what is the strongest reducing agent in this table? What is the strongest reducing agent? Now, reducing agents get oxidized, so you better be picking something on the product. And you want it to be the most positive. Remember, you got to flip these signs yourself, because you're now talking about the reaction going the other way. So whoever said CO is right. Right? The strongest oxidizing agent would be, Hg plus 2. Okay. The max K, work. What are the units for work? Oh yeah, what are the units for work? That's a good question. Albert, what are the units for work? Work is actually the transformation of energy from one form to the other. The form you end up in is usually useless, but still. Work is energy, so work would be joules, right? Okay. If W max is the maximum work that can be obtained from a galvanic cell, what's N? Is it the same N we were talking about from before? Yeah, it's the same N. So it's just the number of moles of electrons, right? And how would you get it? Well, it doesn't really matter. If you know what the half reaction is, and they said, oh, hey, you got 68 grams of copper, you just use your, what is it called, bridge, to get it to moles of electrons. Mole bridge, right? There's 1 mole of copper for every 2 moles of electrons. So you can get moles of electrons, no big deal. Figure out what it is, and that number is what goes in for your little n. And the F, remember, that's the 96,485. What is this? What is that again? A lot of fancy words for it. But where's it found? Volts found on the voltmeter, right? They have to measure it. Okay. have to measure it. Okay. For the reaction, copper plus 2 plus nickel solid goes to nickel plus 2 and copper solid, what is the maximum work under standard conditions that can be performed if 63.5 grams of copper is formed? Okay. So logic to me dictates start with what they're looking for, and then that kind of minimizes your work, right? Work. Huh? So W max, we said was minus NF E cell. Right? Isn't that right? Yep. Okay. So that's all we need to find are those three. Sochi, where would you start? What's that? Okay. Well, they gave us the reaction, but we're going to need the half reactions. We don't know what the mole bridge is, right? Because I don't see any electrons up there. And all you need is one of them. And we're interested in copper solid, so write the half reaction involving copper solid. Copper plus 2 electrons goes to copper solid. Okay. Keep going. Kevin, now what? Now what? What's that? What do you want to do? We want to figure out the maximum work, so we got to figure out what these three are. Someone said to write this half reaction, which we'll need. Get the moles of copper. Sounds like a plan. 63.5 grams of copper. And then what is it? 63.5. Thank you, sir. Oh, it's exactly the same. Okay. But do I want to stop there? No. Yeah, because I need the moles of electrons. I need to find little n. So someone told us to write that half reaction. So in 1 mole of copper, 2 moles of electrons. Stop there? Definitely stop there. That is my little n. Okay, we've got that. Oh yeah, they cancel, don't they? Okay. You got the n. Now what? Get an idea, Jamie? The F. You know what the F is? Well, what is F? What number was it again? 96,485. So you know what F is? Okay, we need, Javier, we need E cell. Table. So that's the copper half reaction you're saying? That's 0.34. Is that my E cell? You have to add up the other one to get the overall, right? You got to make sure those electrons cancel and all that stuff. Okay. So what's the other one? Nickel solid going to nickel plus 2. I think we looked this up once already. Plus 2 electrons. And its voltage was, where was that? 0.25. Thank you very much. 0.25. So we get 0.59 volts. Now the reason why we had to find E cell this way. Oh, it is? Yeah. 0.15. Okay, so that ends up being 0.4, right? Oh, we looked up the wrong one. Copper plus 2 going to copper solid. Here it is. Yeah, make sure, because that's a common mistake. I'm glad that happened. That's a common mistake. People don't realize, oh, that's a solid, right? So it needs to be 0.34. Dagnabbit. 0.34. I thought I had an eraser on here. There it is. So it is 0.59. Okay, that's my E cell. Usually they tell you what E cell is from a voltmeter. But that's why they had to say standard conditions, because you're finding E cell from the table. Okay. Then you multiply it all and you get your answer in joules, right? Okay. So here's our homework. So we can get started on this and see how far you can get. So give it a shot, and I'll be glad to help you out as you're working along here. We've got about a minute. But hopefully we gave you enough information to get started. I've got 2 no names for homework.